Good morning, everyone. Let me remind you of the proposed program. The planned program was that yesterday I would talk about dark matter and finish, and today I would talk about dark energy, and on Friday talk about inflation. However, today we're going to see Rocky 1.5, and I'm going to continue talking about dark matter and hopefully get through most of dark energy. But my feeling is, since these are academic lectures and I don't have to cover any particular material for you on the final exam, I'll take my time and go at what I consider a leisurely pace and in some detail rather than just blasting through and trying to cover everything. So if I don't cover everything in the universe, I'll have to come back and finish it. So we were talking last time about particle dark matter, the idea that most of the mass of the universe is in the form of a yet-to-be-discovered particle, and I talked about mostly thermal relics, neutrinos, stereo-neutrinos, gravitini, and then I suggested that the most promising possibility for dark matter is that dark matter is in the form of a WIMP, a weakly interacting massive particle. And I talked about two examples, the lightest supersymmetric particle and the lightest Kaluza-Klein particle. But the idea of a WIMP is more general than any particular model. And a attractive feature of the WIMP is that its present contribution to the mass density is determined by its annihilation cross-section in the early universe. So if it has an annihilation cross-section to quarks, if it interacts and annihilates to standard model particles, including quarks, then if you know the annihilation cross-section, it gives you some information about the scattering cross-section with quarks and the production cross-section that you would have, for instance, in colliders. So this was recognized 27 years ago when Goodman and Witten proposed that dark matter candidates that are around, the relic dark matter that's all around us, there are millions of dark matter particles, if they're WIMPs, in this room as we speak, going through us at about 300 kilometers per second, that with sufficiently sensitive detectors, one might be able to detect the relic background WIMPs. And in fact, this was shortly taken up, and 25 years ago this month, 25 years ago, was the first report of the first experiment for direct detection looking directly for the WIMPs that surround us. So this month we'll celebrate the 25th anniversary of the first report of an experiment looking for WIMPs. Today there are dozen, maybe more than a dozen experiments throughout the world that are trying to detect the background WIMPs. And here's pictures of just a few of them, but there's many more. There's too many to put up pictures on one slide. I just use some to illustrate that people who look for WIMPs dress up in funny costumes. People wear hard hats just in case a WIMP happens to hit them in the head. You know, it's a little protection against WIMPs. And WIMPs may smell funny, so you have to wear breathing apparatus. These are sensitive, low background experiments. Low background also implies low signal, so you have to be patient looking for WIMPs. So the usual assumption in direct detection is that the local WIMP phase space density will your detection of WIMPs depends upon the local WIMP phase space density. Both the number density of WIMPs that are around us here and the velocity distribution of WIMPs. The usual assumption, the standard assumption, is that the dark matter density in the vicinity of the solar system is about 0.3 GeV per cubic centimeter. So the flux of WIMPs, the number density of WIMPs around us, and the flux of WIMPs would decrease as 1 over the mass of the WIMPs. So the mass density, we believe we have determined or estimated to be about 0.3 GeV per cubic centimeter. Also important in WIMP direct detection is the velocity distribution of the WIMPs. If the WIMPs have a higher velocity, they're going to impart a larger recoil in whatever it collides with, so it depends upon the velocity distribution. The usual assumption is that the WIMPs have a Maxwellian velocity distribution in the galactic rest frame. This may not be exactly true. There may be streams, high velocity tails, we don't know, but the usual standard assumption is a Maxwellian velocity distribution in the galactic rest frame. These are assumptions which should be, and they are, constantly probed and discussed. Recently, there was a paper just last month looking at something that's known as the Oort limit on the density of matter surrounding us. So the model of our galaxy is that there is a bulge, a central bulge, a thick disk population of material, and a thin disk population of material, and the solar system is, again, 8.5 kiloparsec from the center of the galaxy sitting in the thin disk. So it was pointed out a long time ago by Jan Oort that if you look at the oscillations of stars about the disk, you can estimate the surface mass density of the disk. It's just high school physics. And you have to make assumptions about these various astronomical assumptions, but you can infer the local mass density around the sun by looking at the velocity distribution of stars in and out of the plane of the galaxy. This is not so easy to do. There are a lot of assumptions that go into it, and making one set of assumptions, these astrophysicists came to the conclusion that there's no evidence for dark matter around the solar system. This doesn't change the conclusion that there's evidence for dark matter in our galaxy, but we don't know about the local dark matter density, neither the phase-space density, either the velocity distribution or the mass distribution. It could be that we live in a local bubble where there's very few dark matter particles, or we may be in a bubble where there's many dark matter particles. We don't know on the scale of solar system how smooth the distribution of dark matter is. I've spoken to several dynamicists who do this for a living, and they say this is a good paper, it should be read, treated with respect, they don't do anything stupid, but they make model assumptions that are perhaps not agreed to by everyone, and you should not accept this as a final word and should not give up looking for dark matter around us. So the fact that the dark matter, going back to the usual assumption, it has a Maxwellian distribution in the galactic rest frame, is a way to look for dark matter, taking advantage of the fact that the Earth is the Earth is not at rest in the galactic rest frame. If the Earth is moving through the galactic rest frame, going around the sun has a certain velocity, then there should be, in principle, an annual modulation in the event rate if you are detecting WIMPs. For many years, there's an experiment in Gran Sasso, Dama Libra, that's seen an annual modulation in the noise in a detector. And if you interpret this as due to the fact that there's an annual modulation in our velocity around the WIMP-C, then this is a fit with a period of 1 year, which you would expect, and the phase of the modulation is exactly what you would expect from the motion of the solar system. So you're not detecting individual WIMPs in this experiment. You can't say that a WIMP was detected Tuesday at 3 p.m. It's just the noise in the detector. There's no doubt it's highly statistically significant that there is an annual modulation in this signal, and there are many arguments and discussions whether it's due to WIMPs or some other effect causing it. We don't know. So this is one hint that, in fact, we may already be seeing some indication that WIMPs are around us. Again, it's not conclusive evidence, but it may, in fact, be a hint. Another hint that we are seeing WIMPs have recently come up from an experiment known as Cogent. And this is the signal from Cogent, the number of counts per kilogram days as a function of the recoil energy. And this is the number of counts. It's very small. There are lines that are identified associated with nuclear decay, radioactive decay lines, and then there's a background that's not explained. And this background here could be due to the fact that WIMPs are being, the interaction of WIMPs with the detector. If this is the interpretation, if this is correct, then this is fairly low recoil energy, so it points to a fairly low mass dark matter particle, fairly low mass WIMP. In this case, the fit was about 7 GeV, and an estimate of the cross-section of the WIMP with nucleons of about 10 to the minus 4 picobarns. This was reported about 18 months ago. Oops, wrong direction. Oh, they also see at very low statistical significance an annual modulation in their signal. They've only been running for about a year. I guess they started in 2009. This was in 2007, so they have maybe 2 years of data. And at low statistical significance, they do see an annual modulation. At least it's consistent with an annual modulation. If they see an annual modulation in the background, it supports the idea that they are seeing WIMPs, and the annual modulation is due to the velocity of the Earth in the WIMP-C. And then just about 8 months ago, another experiment, CREST, reported a limit on the WIMP nucleon cross-section as a function of WIMP mass. And this is from CREST, the exclusion limit. But they do see regions where there is some indication, again, at low statistical significance of a signal. So you could interpret, it's either a statistical fluctuation, or you could interpret, for instance, this region as being due to a nuclear recoil caused by a WIMP. Also here is the Cogent region and an indication of where you would fit the Dama Libra results, either over here or over there. So perhaps some common, if you put these together, and again, everyone appreciates the danger of combining different experiments. Each of them have low statistical significance, but nevertheless, theorists are not afraid to do this. My colleague Dan Hooper and collaborators have proposed that, in fact, this is evidence that there is a dark matter nucleon cross-section of a couple times 10 to the minus 3, a couple of times 10 to the minus 4 picobarn cross-section, and again a fairly low mass for the dark matter WIMP of 6 to 7 to 8 GeV. This is lower than one would have expected. One would have expected the WIMP to have 30 GeV, 100 GeV, more of a weak scale mass, but perhaps the WIMP has a low mass. And again, these are just hints. Just to complicate or make the situation interesting, There are other experiments, like CDMS and xenon, that seem to exclude this region. So this is the limit from CDMS and xenon on the cross-section as a function of mass, which seems to exclude the region seen preferred by cogent and the region preferred by Dama. There's a lot of discussion in this particular community about the sensitivity and the normalization and the calibration of energies at very low energy scales, and there's a lot of discussion going on now. And in fact, there's been a recent paper just last month from Juan Kolb and Fields looking at the CDMS data and saying there's evidence in the CDMS data for a low-mass WIMP recoil energy at very low mass. And again, everyone appreciates the danger of experimentalists analyzing the data from an experiment they weren't on and claiming to see something. So right now, I think the situation is best described as chaotic, exciting, a lot of confusion. I think it would be a big mistake to really say, of course, no one is saying dark matter has been discovered, but yet I think it would be a mistake to completely ignore these hints. Maybe is the first indication of dark matter. That's the situation in direct detection of dark matter. Let me now turn to another way of testing the idea of dark matter. Again, this idea is not new. 34 years ago, there was a paper pointing out that if dark matter is around us, it should accumulate into the galactic centers of galaxies where the dark matter density should be large, and the dark matter can annihilate, producing a signal that one might detect. In this case, it was the gamma ray background. And the idea is in the galactic center and dwarf spheroidal galaxies in dark matter clumps, perhaps accreted into the sun or the earth, WIMPs can be annihilating today, producing quarks, leptons, and bosons, and the quarks, leptons, and bosons in turn decay, fragment into something that's detectable. And the detectable signal might be low energy photons, medium energy gamma rays, positrons, electrons, neutrinos, protons, antiprotons, the kind of things you would imagine from a high energy annihilation. So the goal of indirect detection experiments is to look to the galactic center, look for something coming from the center of the sun, looking in other galaxies, to see whether there is a signal that you can identify as being the annihilation products from dark matter rather than some astronomical signal. And there are a lot of experiments all over the world and in space from very inhospitable places in the world like Antarctica, the South Pole, Namibia, other inhospitable places like Arizona. And in space, AMS is now flying. There were balloon experiments, satellite experiments, all of these looking for some signal that dark matter is annihilating somewhere in the universe and looking for that signal. So the indirect detection of the annihilation product of dark matter depends upon not the WIMP density around us today on Earth, but the WIMP density in the galactic center or other structures. The simulations are unable to resolve on small enough distance scales what the expected dark matter density in the center of our galaxy would be. And when I say the center of the galaxy, I mean the inner parsec or so of our galaxy. And then to take this into account, one often employs something known as a boost factor. A boost is a better word than a fudge factor. People just say, well, maybe the dark matter density is 100 times larger than what you would expect. They call it a boost factor because it boosts the results of their calculation. If you're looking for the effect of dark matter annihilation to positrons, high-energy electrons, or antiprotons, and it's in the galactic center, there's an additional issue that charged particles are dispersed in our galaxy due to galactic magnetic fields. So if you detect a high-energy electron coming from a particular direction, you can't trace it back and say where it came from. And finally, there are astrophysical backgrounds to all these processes. How do we know a positron that we detect originated from dark matter annihilation and not through some energetic process in the galactic center, in nearby pulsars? There are astrophysical backgrounds for all of these processes. Nevertheless, let's explore this, and we see a variety of hints or possibilities that something has been seen. ATTIC is the balloon experiment that measures the spectrum of energetic electrons. So this is energetic electrons at the top of the atmosphere with energies between 10 GeV and a few TeV. Now, what's expected is calculated on the basis of numerical simulations. In particular, there's a standard program called GalProp. And there's a lot of discussion in the community whether this is to be believed, how much we should believe it. It's used by most people. And this might be the prediction of what the background would be. And the ATTIC data, as reported by the collaboration, seems to see something that looks like a peak there. And one way to fit this, you can fit this with a peak over a smooth background. And in this particular paper, it's fit by the annihilation of WIMPs with a mass of 620 GeV. So the direct detection experiment hints point to 6 GeV. This would be something much different than that. It's not the same phenomenon that's being seen. There is a space experiment, Pamela, that measures the positron flux, and this is normalized to the positron flux divided by the positron plus electron flux. And this has been measured by several experiments before Pamela. And again, this is an estimate of what the background would be. And it seems to be an anomalous signal here that's not explained by the expected background. And this is an energy of the positron of 50 or 100 GeV. And there are models that fit this by the annihilation of neutralinos of mass 130 GeV, 230 GeV, various ways to fit this. So this is not evidence or proof, but perhaps it's a hint in something in the positron spectrum. Again, these are not so much low statistical significance as the direct detection experiments, but rather they are results that are subject to astrophysical uncertainties in terms of what the background would be. The Fermi-glassed gamma-ray satellites has been flying for a few years. The Fermi-glassed collaboration absolutely refuses to see dark matter annihilation, but their data is public, and people have combed through the data, and two groups at least have claimed what they see as evidence for dark matter annihilation. This is the result of a paper by Hooper and Goodenough that analyzed the data taken by the experiment. And of course, theorists are much better at analyzing data than experimentalists because they know exactly what to look for. And they say that there's some sort of bump here in the energy of, these are gamma rays of a few GeV, and they say this is best fit by a dark matter particle which has a mass of 8 GeV that's annihilating, and this is a leptophilic annihilation, and the annihilation mostly goes into tau plus, tau minus. And if you work not very hard, you can find a model where, in fact, this happens. Another group looks at the Fermi data. Again, this is a group of theorists who are not involved in the Fermi experiment, and they look at the vicinity around clusters of galaxies. And there's a gamma ray haze, so they remove galactic diffuse background, point sources, cosmic ray effects, and they claim that there's something left over, and that something left over could be fit by dark matter annihilation. And it could be fit by a variety of possibilities: dark matter in the 20 to 60 GeV range that annihilates mostly to BB bar, or dark matter in the 2 to 10 GeV that annihilates mostly to muons, or perhaps greater than 1 TeV annihilating to muon pairs. It's fit by many things, and again, this is the analysis that has to remove astrophysical backgrounds, and it's the analysis done by people who are not part of the collaboration that actually took the data. Most recently, there's been an analysis. Again, theorists are much better at analyzing data than experimentalists because they see more things. There's the indication in this paper that's just a month old of a line in the Fermi data here with an energy of about 130 GeV. And this is a very difficult analysis, and the resolution of the detector is not as good as you might desire, but there's, again, a paper written claiming evidence of a line at 130 GeV. And in fact, there is a model that had been on the market that predicted this, a model by some collaborators of mine. This would be the annihilation of a neutrino-like particle going through a Z prime that couples mostly to TT bar, and it would annihilate into a photon and a Higgs. And this is what they would predict for the spectrum of gamma rays in the annihilation, and this is in agreement with what is seen, or what is claimed to be seen by this. So it's confusing. There is no smoking gun evidence either in direct detection or indirect detection. So the question is, again, WIMPs point to something of the weak scale. Is this the causation or coincidence? The situation is now muddled. There are hints from direct detection experiments from Dama Libra, Cogent, CREST-2. There are indirect hints from analysis of astronomical data from satellites looking at charged particles or at gamma rays. And now the LHC is beginning to weigh in. So what we'd like to be able to do is to say, if Cogent sees a WIMP that's scattering on a nucleon and tells us what this scattering cross-section is, could you see it? Could you see WIMP production, for instance, in the LHC? This is a non-relativistic scattering, and to get from the non-relativistic scattering to what you would expect from a relativistic scattering is model dependent. So it's not completely clean to say, excuse me, if I see this at low energy in direct detection, to say with any certainty what you should see in a collider. So there are two ways you might do it. One, the traditional way, is to assume that the WIMP is part of a social network, that it has friends. So the WIMP is part of a social network. It's not going to be the only new particle that's seen. It's our experience that every time we explore a new energy scale, we see many particles, not just one. And the way this is pursued is to start with some motivated model, for instance, low energy snoozy. And then in this case, there are many new particles and interactions to pursue. Now, this is an attractive way to proceed, but then there's a muddy relationship between the annihilation and scattering, and the annihilation cross-section, the scattering cross-section, and the production cross-section. It's not so easy to relate them. The other approach is to assume that the WIMP is a maverick particle, that it's a loner, that it's the only new particle that's within reach, say, of the LHC. If this is true, then the description of the interactions between the WIMP and standard model particles you can use effective field theory to describe. And the WIMP would be the only new species at the weak scale. But in this case, there is a clearer relationship between annihilation and scattering and the production cross-section. So an example of how to proceed from Maverick WIMPs is, for instance, assume the WIMP is a Dirac fermion, then you can write the interaction of the WIMP with standard model particles like a quark through a Fermi-type interaction, a 4-Fermi interaction with some effective coupling constant, and it's going to depend sensitively for direct detection experiments on whether it's a scalar, a pseudoscalar, a vector, etc., an axial vector, the type of couplings that you might have. You can also have a complex scalar Maverick WIMP, scalar WIMP, and again, it's some non-renormalizable effective field theory description of the interaction of the WIMP with standard model particles. There is a finite but distressingly large number of possibilities for the couplings of the WIMP with quarks, and you can go through analyzing each one in detail. And this has been done, and you can calculate the value of the effective Fermi coupling constant of the WIMP with dark matter, the WIMP with dark matter that would give the correct dark matter abundance. This is a graph of the coupling constant times the mass as a function of the mass of the WIMP. And it's pretty constant here unless the WIMP couples through a scalar or pseudoscalar interaction where the coupling constant is proportional to the mass of the quark that it couples to. Then you can compare this to direct detection limits. These are the lines that you would expect for the nucleon WIMP cross-section if the WIMP is a Maverick particle that annihilates the quarks. And whether it's a scalar, a vector, a scalar proportional to the mass of the quark, this is the value of the cross-section you would expect if it is the dark matter. And this also assumes that the cross-section, that the scattering at low energy is spin independent of the spin of the nucleon that it's scattering with. This is the limit that's recently been reported by the Xenon 100 experiment, and these are predicted expected limits in the next few years from phase A and phase C of CDMS. Every experiment has new phases that predicts better results. So the cross-section at high mass now is limited to about 10 to the minus 7 or so picobarns here, and it's going to march down to some amazing value like 10 to the minus 11 or 10 to the minus 12 picobarns. So for instance, the direct detection experiments rule out to very large degree the possibility of the dark matter being a Dirac a Dirac fermion that couples with vector interactions to quarks. This has been ruled out for many years, and in fact was ruled out in the paper that I showed you from 25 years ago. So in 25 years, we've marched down, and we'll continue to march down in this limit. This is the result for spin-independent interactions. So for spin-independent interactions, scalars or vector interactions, for WIMP masses larger than 10 GeV or so, the cross-section is limited to be smaller than 10 to the minus 6 picobarns. But around a few GeV, the cross-section could be as large as 10 to the minus 6, 10 to the minus 4 or so picobarns. And let's keep that number in mind because it's going to be interesting for collider results. The situation is somewhat different for spin-dependent scatterings of low-energy scatterings of the WIMP with nucleons. If the scattering proceeds through an axial or a tensor coupling, then this is the result you would expect for the usual dark matter calculation. This is the region that's been ruled out in 2010, and just last month they reported the COOP 4 kilogram result, which is down here. So unlike spin-independent interactions, direct detection experiments have not ruled out axial vector or tensor interactions for dark matter, but it will eventually in the future start to chew away at that allowed region. So if the WIMP is spin-dependent cross-section, you can have a cross-section of WIMPs with nucleons that's larger than about 10 to the minus 3 picobarns and still be consistent with direct detection experiments. And that, I guess, is what I've just said. If it's spin-dependent, sigma can be as large as 10 to the minus 3 to 10 to the minus 6 picobarns and be consistent with data. Okay, so how would you look for these WIMPs in a collider? Let's say if you had a collider nearby, how would you look for WIMPs? Well, if it's a part of a social network, an example of this, of course, is supersymmetry. The cross-section for producing gluinos and squarks are much larger than the cross-section for producing neutralinos. So the way you would see the neutralinos is producing, say, gluinos and following the complicated decay chain that eventually produces a neutralino that escapes the detector, it's undetected, and you would look for some complicated decay chain which ends up having some missing ET. If the WIMP is a Maverick particle where you can describe the interaction of the WIMP with quarks by an effective field theory, you know this coupling constant either from the determination that it gives the correct dark matter density or direct-indirect experiments, so you know that. And the way you would look for this is look for, in a high-energy collision, say a gluon and a quark, producing a jet and missing ET. So it's a cleaner signal, and that coupling is known from direct detection or indirect detection. So the way to look for WIMPs, one way or another, in colliders, of course, is looking for missing momentum, and it could be that missing momentum signals in colliders are the result of the missing mass in the universe. But again, the connection between what you see, what you learn from direct detection experiments, and what you would learn in a collider is model-dependent. This is non-relativistic scattering with this particular cross-section. It's clear that this can be described by an effective field theory. It's not clear that the description at relativistic energies can be described by an effective field theory. But for a moment, let's assume that it can be described by an effective field theory. So you can predict what you can see, what you would see in collider searches, and is a standard procedure that is familiar to most people here. you generate events through MadGraph and MadEvent, run it through Pythia, and since theorists are lazy, you wouldn't do a very complicated simulation of the detector. You'd use something like PGS to reconstruct the events that would be seen at a collider. And this is what we would predict. You can probe the coupling constant at colliders. This is, again, the 4 Fermi coupling constant as a function of the mass. This is what's predicted would be ruled out at the tevatron. This is the prediction of what would be ruled out for 5 inverse femtobarns at 7 TeV at LHC. And if you take LHC with the full luminosity, say limiting it to 100 inverse femtobarns, this is what you would rule out when LHC is running at 14 TeV. And you can probe the cross-sections that you would expect at low energy in direct detection experiments, at least down to 10 to the minus 4 picobarns. And if experimentalists get a little bit smart, you can rule out things as low as 10 to the minus 6 picobarns. And this, in fact, has already been recently done at colliders. The first collider to do this was CDF, that reported it just last December, or just last March, sorry. And this is the limit on the spin-independent cross-section from the collider results. And it rules out something here of about 10 to the minus 3 or so inverse picobarns. And this depends upon whether it's a contact interaction or it's a mediator. And this compares it to, this is for spin-independent scattering, and it compares it to cogent results or xenon results. Colliders, just here at CDF, you have the best limit for very low mass WIMPs, but for massive WIMPs, the limits from direct detection experiments are better. You can also do this for spin-dependent cross-sections. Sorry, this is off the graph. And here, colliders, the CDF result, does better for WIMP masses up to about 6 or 7 GeV. And just this year, CMS, I don't believe Atlas has reported any results like this. CMS has reported results doing a similar analysis, the result on the WIMP nucleon cross-section for spin-independent scattering. And this is the limit from CMS, both for monojets or monophotons, compared to what is deduced from the direct detection experiments for spin-independent scatterings. And again, colliders do much better for limits of a few GeV, but if you go above about 10 GeV, the limits that you can get from colliders are not as good as the limits that you can get from direct detection experiments. The situation's different for spin-dependent interactions. For spin-dependent interactions, the colliders are about as efficient as for spin-independent interactions. The collider results are very insensitive to whether the interaction is scalar, vector, or axiovector, but the direct detection experiments are very sensitive. So here, in fact, the collider results are better than the direct detection results up to masses of about 100 GeV. So if the, just let me point out that if the, let's go back here, for spin independent, if the WIMP is a low mass WIMP of 6 to 8 GeV, as suggested by Cogent, Dama Libra, and Crest, you can argue that putting these things together point to a very low mass WIMP, with a spin independent cross-section of order 10 to the minus 4 or 10 to the minus 6 picobarns, this will be within range of LHC running at the full energy and full luminosity. So there are questions about this WIMP picture for dark matter. One question to ask is, so far, we've assumed that there's only one new species of WIMP, only one WIMP species. Let me remind you that most of the mass of the universe is in the form of dark matter, which we are assuming is a WIMP. So the small fraction of the universe that's not interesting, that's not in the form of WIMPs, is quite varied. There are neutrons, protons, photons, neutrinos, electrons. There's a rich variety of particles that are around in the part of the universe that we do see. Why in the world should we assume that most of the mass of the universe is simple and in the form of only one species? If there is a social network of several stable or very long-lived new particles, then the stronger interacting ones are easier to detect, they're easier to see, but the more strongly it interacts, the smaller its contribution to omega will be. So if you do convincingly see something at a collider, if you see something in direct detection, if you convincingly see something from indirect detection, how do you know that the particle that you are detecting is actually most of the dark matter, but is not some other component, smaller component of the dark matter, if there's more than one WIMP? There's also theories that involve things known as super WIMPs, where the particles that are the dark matter today are not produced directly through the annihilation in the early universe, as in the usual calculation that we've been doing, but rather is produced by the production of another particle which decays much later to the WIMP. So then, it's a way out of relating the density of the dark matter to the annihilation cross-section. Why do we assume WIMPs do not interact with themselves? Perhaps WIMPs are self-interacting. That would have an impact in how we look for them. Most calculations involving WIMPs assume some universal couplings to quarks and to leptons, but perhaps the WIMPs are either leptophilic and like to interact with leptons, or perhaps they don't interact with leptons at all. Perhaps they're lepton phobic. Perhaps the WIMP couplings to quarks or to standard model particles are flavor dependent. Another possible complication that makes it more difficult to interpret the experiments and relate the predictions to the experiments. Finally, there's the experimental issue of maybe there's a haze around the galaxy that's due to the WIMP annihilation. People look for hazes, fogs, and mist. I think of this as the typical Geneva weather, but maybe the typical Geneva weather describes the environment around the center of our galaxy. All these questions and complications are just for WIMPs. I think that this next decade will be the decade of the WIMP. The WIMP idea has been around for 35 damn years. Finally, in the next decade, with LHC turning on, direct detection experiments finally getting to the sensitivity that one needs, with the large array of astronomical observations for indirect detection, it's hard for me to imagine that 10 years from now, a WIMP that we do not have convincing evidence for it, or the WIMP hypothesis will have a near-death experience. It's always possible, theoretically, to invent a WIMP that somehow would escape direct detection, collider production, indirect detection. But 10 years from now, people will either know that WIMPs are the dark matter, or there will be very little interest in them. Direct detectors, indirect detectors, and colliders are racing for discovery of the WIMP. And suppose in another few years, by 2015 or maybe 2020, we have credible signals from all three. How will we know that they're all seeing the same phenomenon? How do we know that a WIMP detected at LHC is actually the dark matter? How do we know that that's related to the indirect detection results? There are lots of opinions or papers about this, and I think let's all hope for this problem. So in terms of WIMPs, I would say that the existence and understanding dark matter is a complicated physical phenomenon. And WIMPs may not be the answer, but WIMPs are a simple, elegant, compelling explanation for a complex physical phenomenon. I once gave a colloquium, and Tommy Golds pointed out to me that for every complex physical phenomenon, there is a simple, elegant, compelling, wrong explanation. So just the fact that WIMPs are simple, elegant, and compelling does not mean it's right. We have to experimentally determine whether it's right or not. So how will we solve this issue of whether WIMPs are the dark matter? I don't think it will be settled by any one experiment or any one type of experiment. I don't think it will be settled completely by direct detection experiments or indirect detection experiments or even in results from colliders. I think to really solve this problem that goes back to the 1930s, it's going to require the work of many different groups connecting colliders and direct detection and indirect detection and model building and theory and cosmology. It's not going to take any one group. It's going to take a village. It's going to take a village people. In fact, it may take the village people to do this. So this is a group of people looking for WIMPs. There's the CERN director, the chief of everything, cowboy cosmologists, experimentalists with hard hats, members of the Swiss Army. Here's the Beyond the S&M guy, and Susie Copps. It's going to take the village people to learn about dark matter. That is the end of my first lecture, so now I'll start the second lecture. Before starting the second lecture, just let me ask if there are any questions, any wimpy questions. Yes, sir.
Could you comment a little bit more on the cogent and the crest? What are the main backgrounds?
So the question is the cogent and crest experiments, to comment more on that, and what are their main backgrounds. Let me get to it. So there are very different type of experiments. Cogent is an experiment that is a germanium crystal. It's a special type of germanium. My colleague Juan Kolb works on its P-type contacts or something like that. And it's a very low background experiment, but here you're looking at extremely low energy nuclear recoils of 1/2 of keV. And there are nuclear lines and things like that. They think they've isolated those. It's a very high-resolution detector. And they see events at very low energy that they cannot explain by any other explanation. So they see something they cannot explain yet. So whether this is just something having to do with background in the detector, some radioactive contamination, or something that they don't know about, a loose cable. No, that's neutrinos that have loose cables. But something like that, it's a difficult experiment. They're building larger. They're running more. They do see an annual modulation. That's a good sign. It's still unknown. The crest experiment, again, is running at very low recoil. I don't show the recoil energy, I show the mass of the WIMP. And there are backgrounds there, and both of them are not golden 5 sigma detections. So these are low statistical significance in regions that's really pushing in the edge of what they can do. And one of the things you learn is that every experimentalist who works on one experiment can tell you exactly what's wrong with every other experiment. Any other questions? Wimpy questions? Yes?
The phase of coordinate and gamma are in agreement?
Are they in agreement? If you look at each experiment and say, what is the region, again, it's a statistical significance issue, there's some region that's 2 or 3 sigma, and they don't quite overlap. But again, the normalization's difficult, the calibration and things like that at low energy. So that's why theorists come in and say, gee, if we move this region a little bit this way and move this region a little bit that way, it overlaps. It's really difficult to say whether they really overlap or not. It's not inconsistent to imagine that cogent, crest, and gamma are overlapping, but it's not obvious. Other questions? Yes?
The collider exclusions all cut off at 1 GeV. And as an experiment, it's not obvious what happens at 1 GeV. Is there a theoretical limitation to not set limits below 1 GeV?
Well, they just don't look at things below a GeV. I don't think there's any particular reason to cut it off at a GeV, but who could imagine a WIMP smaller than a GeV? I don't know. Is there anyone here on the CMS analysis? Steve was here yesterday, but he's gone. One of the ways, so there, in addition to looking for the WIMPs in the monojet, one of the largest backgrounds are the nu bar production that would produce a monojet. Now, if the WIMP is massive and you're at high energy, then and you cut on a high enough jet PT, then you're looking at high energy processes where nu bar production is decreasing. But since this would be described by a contact interaction, the cross-section for that increases as S in the parton level. Then you have to propagate that through the fragmentation and Pythia and all that. So you're most sensitive in these experiments to larger mass WIMPs, which would have a larger PT that you could produce. But I don't know why they cut it off at 1 GeV. And they do also here. Other wimpy questions? Well, I have now finished the first lecture. So tomorrow I will talk about dark energy, hopefully finish dark energy. I have less to say about dark energy because less is known about dark energy. And I guess I won't talk about inflation. There'll be another academic training exercise someplace where someone comes in and talks about inflation. So thank you. Tomorrow's dark energy.